So, when you think of a black hole, you probably picture a cosmic vacuum cleaner, right? This massive point of no return that just swallows everything. And you know what? You're not wrong, but that is only half the story. The simple black holes from the textbooks, yeah, they're cosmic sinks. But the real ones? Oh, they're engines.
Let's just start with a really wild question that kind of flips the whole idea on its head. What if you could not only avoid getting eaten by a black hole, but you could actually steal energy from it? What if the most destructive things in the entire universe are also its greatest source of power? Let's dive in.
To even begin to understand how that's possible, we need to upgrade our mental model of what a black hole is. We've got to move beyond that simple version we all learned about.
See, this is the classic textbook black hole. It was first figured out by Karl Schwarzschild using Einstein's equations. And it's perfect. Perfectly spherical, doesn't rotate, and you only need one thing to describe it: its mass. It's simple, it's elegant, and it almost certainly doesn't actually exist in the real universe.
Because here's the thing about our universe. Stuff spins. I mean, stars spin, galaxies spin, giant clouds of gas spin. So when a really massive star collapses to form a black hole, all that spin, it doesn't just disappear. Nope, it gets concentrated, and it creates something that is fundamentally different from that simple, perfect model.
So we need a new model. The simple one is just defined by mass, which we call m. But the realistic one, that's called a Kerr black hole, and it's defined by mass and spin, its angular momentum, or J. And trust me, adding that one extra parameter, it changes the entire game.
Which brings us to the real star of our show, the spinning, dynamic, and frankly, super bizarre Kerr black hole. Just look at that time gap. It took nearly 50 years for physics to catch up. Schwarzschild found the simple solution way back in 1916, but it wasn't until 1963 that a mathematician named Roy Kerr finally cracked the incredibly difficult equations for a rotating black hole. And today, his solution is absolutely fundamental to astrophysics.
Okay, don't worry, there's not going to be a math quiz. Think of this equation, the Kerr metric, not as some problem you have to solve, but as a map. This is the precise mathematical description of the warped, twisted spacetime that's all around a spinning black hole. And it's this map that predicts all the strange stuff we're about to get into.
So, what does this map tell us? Well, it tells us that a spinning black hole doesn't just curve spacetime. It grabs it, it twists it, and it drags it along for the ride.
And right away you see the first huge difference. The event horizon, the point of no return, it isn't a sphere anymore. The intense rotation causes it to bulge out of the equator and get all squashed at the poles. Kind of like what happens when you spin a ball of pizza dough.
But this is where it gets really weird. See, even before you reach that point of no return, you have to cross another, even stranger boundary. It's a region where the normal rules of space just kind of break down.
So yeah, a Kerr black hole has two of these key surfaces. The inner one, that's the familiar event horizon. But outside of that is another boundary, and that space in between them is called the ergosphere.
The name itself is a huge clue. Ergo comes from the Greek word for work. This is the work sphere, a region where the black hole's spin is so incredibly powerful that it literally drags space-time itself along with it. It's like a cosmic whirlpool made of pure space-time.
I mean, just try to wrap your head around what that means. Inside this region, you physically cannot stand still. It doesn't matter how powerful your rockets are, space-time itself is flowing past you, and you have absolutely no choice but to get dragged along with the black hole's rotation.
And now we get to the heart of it. That work sphere? Well, that's the key to pulling off the greatest heist in the entire cosmos, stealing energy directly from a black hole.
This absolutely mind-bending idea was first dreamed up by the brilliant physicist Roger Penrose. He realized that this ergosphere thing wasn't just some weird curiosity, it was a place where you could, in theory, tap into the immense rotational energy of the black hole itself.
All right, so let's break this down. Imagine you send a probe into the ergosphere. Then, at just the right moment, it splits into two. One piece is aimed so that it falls into the black hole. Now, because of the bizarre physics in there, this piece can actually have negative energy from our point of view. So to keep the books balanced and conserve energy, the other piece has to fly out with more energy than the original probe started with. So where did that extra energy come from? The black hole paid for it, slowing down its spin by just a tiny, tiny amount.
And you can see the basic idea right here. A particle goes in, it splits, and one piece falls in while the other escapes with a huge boost of energy. You've essentially turned the black hole into a cosmic slingshot, and it's powered by its own spin.
Okay, so the Penrose process is a beautiful piece of theory. It's a great thought experiment, but does anything like this actually happen out there? Does nature really use this principle to power the most extreme events in the universe?
Well, the idea of splitting particles is really cool, but it's hard to see how that would happen on a grand scale. Turns out, nature has an even more elegant and way more efficient method. It's called the Blandford's-Nyjek mechanism, and it's what scientists believe really turns these spinning black holes into cosmic power plants.
So the key here isn't particles, it's magnetic fields. This process uses the magnetic fields from all the gas and dust swirling around the black hole. The black hole's insane rotation grabs onto these field lines and twists them up, acting like a colossal electrical generator. And that's what launches these incredible jets of charged particles out from the poles at nearly the speed of light.
And we're not talking about some small effect here. This mechanism is the leading explanation for some of the most luminous, most violent things we see in the sky. I mean, things like active galactic nuclei and quasars, which can outshine their entire host galaxies, are probably powered by supermassive, rotating black holes. It's the engine behind those spectacular plasma jets that can stretch for millions of light years across space.
This idea really says it all. This isn't just theory anymore. It's the framework that connects Roy Kerr's abstract math to the breathtaking images we get from our telescopes. The cosmic destroyers are also the cosmic creators, driving the evolution of entire galaxies.
So, we started with a black hole as an endpoint, right? A place where things just vanish. But now we see that for rotating black holes, that just isn't the whole story. They are dynamic, incredibly powerful engines that shape the cosmos on the grandest scales imaginable. It really makes you wonder, if our basic understanding of black holes was this incomplete, what other secrets are hiding out there in the dark, just waiting for us to ask the right question?